Okay, so how do we figure out what t value to use in our confidence interval? Well, let's look at this an example here. For a 95% confidence interval, where n equals 22, the size of our sample is 22, then alpha here is equal to 0.05. So essentially I got that from 1 minus 0.95. Then alpha over 2 equals 0.025. So that means then, if I draw a picture here, the area here is alpha over 2 is 0.025. Okay, that's important to know. This is 95%. This is 2.5%. Then to use this table, I need to enter the table at a value of t of 0.025. Now, notice on this table here that they're calling this alpha because we're going to use this table in a number of different ways. Sometimes this left tail will actually represent the alpha we're interested in. But in our case, it's an alpha over 2. So really what you need to consider here, this is, so I'm just going to put in this case to use this table. And you have to know this, you have to understand what you're doing in order to interpret any particular table correctly. But for this case, in this case, alpha here is going to equal 0.025. But it's not the same as our alpha over 2 alpha. But it's the same. It represents this area, which is the same as this area here, and that's what the table is going to calculate. It's going to calculate the t value, the left boundary of this area, which is going to be our t value, and that is the same thing as t of 0.025. So the way we do that then is we find our t of 0. And that's this t now. So we know what t we're looking for. Now we come down here with degrees of freedom. We haven't calculated that yet though, but degrees of freedom for this problem then equals n minus 1 equals 22 minus 1 equals 21. It's always going to be n minus 1. That's this value here. So we come in over here, we come down here, we settle on t of 0.025 equals 2.080. And that's simply how we do it. That's how we're going to get to t. So that t value now, if we had a problem, would go in here instead of z. We put our t value in for that value. So that's how you use the t value. So you'll notice the t values, the subscript on the t's, are only for a couple different types of confidence intervals. We'd have the confidence interval of a 98%, a confidence interval of a 90%, confidence interval of 80%, and you can back calculate what these alphas are, why these alphas represent those sorts of things. So so this table now is not as extensive as our other table, for our z table. So it's only good for certain types of confidence intervals. And of course, you know, when I give an exam or something, I will only give you a confidence interval that you can get off of this table. Now, if you were to go to the internet, you could find t values that way too, in the same sense, using the alpha and using the degrees of freedom. You could go and you could look up a t table on the internet, and it would be a much broader table. If you put the values in, the computer would have a much larger data set that it could pull from. So you could have all sorts of different types of confidence intervals that you could find the t values for. So let's do an example problem. So let me pause and write the problem question down here. Okay, here's our example. Say we do destructive testing on printer heads. We're a printer company and we're trying to figure some stuff out about our printers. We want to find the average number of characters before failure occurs on our printer heads. Now, we're a company and we're in business to make money, so we can only afford to run to failure 15 printer heads. So we take 15 printer heads and we run a little experiment, and we run them until they fail. And out of that sample set of 15, the average is 1.23867 million characters printed before they fail. And the standard deviation of this sample is 0.1936 million characters. So how do we approach this problem? Well, the first thing we want to do is let's start drawing some pictures. So one of the first pictures I would draw is what's going on here. So we have printers that fail, and we are looking for the average number of characters. But we only took a sample of 15 to try to figure that out. So our sample could end up somewhere on this side, somewhere on this side of the mean. You know, it's hard to say where it is. But we're going to set up a 99% confidence interval. So this is a little higher than what we did before. A 99% confidence interval estimate of our mean. So let's start out. So maybe one of the first things I do doing these problems is I figure out what alpha is. So alpha here is, see if you can guess it, maybe pause, 0.01. Then alpha over 2 equals half of that, 0.005. So that's associated with way over here. We're going to have a t of 0.0. Well, actually, t's not on this curve. T would be on the standard normal curve. But this area is alpha over 2. This blue area that I have shaded in is alpha over 2. And then I always do degrees of freedom at this point, degrees of freedom, because I like to have all these numbers here so I can look at them. So degrees of freedom is n minus 1 equals 15 minus 1 equals 14. Okay, so I've got that basic ideas. So in order to solve this problem, I'm going to need to look up t of 0.005 for degrees of freedom 14. So I can do that right now. So page up here. So t is 0.05. Let's pick a different color that stands out. Let's go with orange. Okay, so orange. So here's t of 0.05, and then here's 14. And we cross-reference this, so our t value is 2.977. So we're going to use this in our confidence interval. Equals 2.977. Okay, so now my confidence interval, I'm going to write this a little different than I did before. Not with the equal sign, but I'm going to write it like I have this way. It's going to be x bar plus or minus our margin of error, which is going to be t of 0.005 times s over square root of n. Just simply that. So now our x bar is 1.2 0.3867. That's our sample mean. I don't know why I wrote it up high like that. I can slide it down, I guess. If I can get a... Okay, we'll use the mouse. Let's bring her back down. Okay, this is then plus or minus. You'll have to scroll up on your own here. Our standard deviation was 0.1936, and we divide that by square root of n, or square root of n here was 15. Now notice n is 15 even though our degrees of freedom is 14. That's a common place to make a mistake, so don't make that mistake. So I end up with mu equals 1.2387 plus or minus 0.1484, barring any calculation mistakes. And I can write that in the other form that we use, where I take this number and I subtract off 0.148, and I do that, I get 1.09 is less than mu is less than, I can add this number to 1.23867, and I end up with an estimate of about 1.39. So these are our answer. This is our answer. Put it in any form you like. So what I did was, with I am 99% confident. I'm 99% confident that our population mean, or the average amount of time that our printer heads will last, between 1.09 million and 1.39 million characters. And I can take that number and I can put it in our brochure for our printer head. Okay, so that finishes up our section on confidence intervals. And I'm going to end the video here.